My name is Brian Wang. I've been involved with Foresight since the mid-90s. I'm now working with the Center for Small Cell Nanotechnology, the task work group put together Mike Treader and Chris Phoenix, and now Jermaine Cavio, I think, is involved with that. I have a website, advancednano.blogspot.com. Okay, so I'm going to talk about converging technology, just my ideas around how to kind of look at it and try to think about opportunities that could be taken advantage of. One is that I can consider it somewhat like Web 2.0 mashups, where you have currently you have web services like Google Maps, and you have other location information databases, and you can combine that up to create a map of real estate prices or rental prices, and it can be done very easily. So I think the main thing is that you're saving a lot of time and money to get to a particular solution by combining some things that are already there, things that are improving rapidly, or just taking advantage of new capabilities in different ways. So versus somewhat even matchups, you're looking at broader levels of technologies, different kinds of methods to get to different kinds of applications, kind of bigger view of matching things up. And you definitely want to get something that's cheaper and sooner. If you wait until molecular manufacturing arrives, then with now factories and that kind of thing, then many things become very cheap and very easy to do. The good thing about convergence would be that if you can figure out a way, well, how can I do that now or very soon? How can I get to something very interesting that happens, that becomes easier to do by combining some things together in an interesting way. And the bigger your toolkit is, then the more possibilities you can attack. And also, you have to have a bigger view, detailed view of possible problems. So the bigger toolkit is to know all the technologies that are coming down the pike or already available. And at my website and other places, you can, any kind of futures website, you might be able to see all sorts of new technologies, new materials, the metamaterials, the super lenses, the things also like the new thing they're doing with viruses and DNA, a long list of those kinds of things. So the more you know about those things, then the more you can apply something in an interesting way. And I will give some examples of some of the ideas that I've come up with around applying a lot of technology that I've looked at into something that I think could be interesting. And of course, the more properties and effects you look at, then also the better that is. Properties and effects I'm talking about are not just strength of material, but things like magnetic properties, optical properties, and being able to use those in the mix. Some improving technology I think is underestimated are the labs on a chip, bubble logic. They have something developed at MIT. So the labs on a chip are where you have a piece of silicon and you've etched into it a bunch of pathways. So you have a bunch of reservoirs which hold like a small amount of material, liquid material, and then you can move it over and combine it and do a lab reaction. Bubble logic is where you do the same kind of thing, but you use micron size or smaller bubbles, and they go around these pathways, these pipes on your chip, and they can go a lot faster. They can get up to 1/1000th the speed of a computer chip electronically. So they're just a lot faster and more flexible because you can treat them more like a liquid version of a computer. Nanomaterials are revolutionizing. There's superconductors that are coming out. They're doing. They still aren't at room temperature, but they are being used at the utilities to create. Yes.
Is the bubble one algebra ground holes?
I believe it is. Yes. So they can do operations on it. It still has to have transition time and various other things, but it seems that they can do logical type operation. But it's just moving the bubbles around to create the effect. But it basically seems to be, I view it as a better version of lab on a chip. You know, better versions of capillaries, better versions of that. That's why I view it. And I admit that there could be something in the details of some of these technologies. I cover a lot of them, which I may be lacking some critical understanding of them. I don't say I'm a PhD in everything. You know, I cover a lot of stuff, and I go to a fair bit of depth. I read the papers. I try to understand them, but I could be missing something. It won't be because of lack of effort. That's the case. Some of the technologies underestimated, I think, are nanomembranes. I think those things are happening now. I think, you know, Gale's her company is doing a lot of interesting things with those. There's a lot of other companies that do interesting things with nanomembranes. They also are using nanopores to sequence DNA a lot faster. That's something that's dropping in price a great deal. So where you run DNA through a small hole, and then you can check the electronic differences to see whether it's one of the 4 different elements. You can then read the sequence a lot faster. So if you have a lot of pores, you can do that a lot faster, and maybe you can bring the cost of sequencing DNA from $1 million, $100,000 for a whole genome to $1,000, $100, and a lot less. So those kinds of rapidly improving things, many of these things improving faster than Moore's law, are things that you can look at as, you know, clearly a lot of interesting things happening there. You could use it in ways unintended or combine it with something else. Lasers. Lasers have been around a while, but you have new things you can do with them. One is there's femtosecond lasers, which are very short pulses, and basically you can pretty much almost disintegrate something off a surface because the reaction time is so fast. You can just kind of blast it off. And you can do all sorts of different things in terms of reactions and timing and stuff like that with the femtosecond lasers. Wireless, I think, is underestimated. Robotics, there's 4.5 million robots around, I think, the United States, something like that. And there's the robots for vacuum cleaners in the industry and in UAVs. So it's an area that I think is kind of in the back of people's mind, but they've kind of overlooked it, I think, for how you can converge technology. And there is the early stage versions in production of what we'll get with nanofactories. This is rapid prototyping, rapid manufacturing, something called Claytronics. So rapid prototyping and rapid manufacturing are here now. And basically they're close to $1 billion industry, if not more. And basically you have devices, some small desktop, others, a couple of refrigerators, which are used, they use different ways to do it to make fairly precise products. The prototyping version is a relatively inert 3D object, which is a mock-up. The manufacturing is electronics, where it actually works. You actually make a working camera or something like that. The issue with manufacturing is that you want to do short runs, so it's cheaper. So anyway, so there's a long list of technology that you want to know. The more you know, the better then you can be at it. So let me talk about an idea that I had for convergence technology opportunity. We had this morning's talk with Matt Francis from the University of Berkeley. He was talking about using cells or viruses and bacteria to create anti-cancer therapies in the body or solar cells. My thinking is that you could apply something similar to the ocean. The ocean has a lot of material in it that you want. There's uranium, 4 billion tons of uranium in the ocean seawater. There's also a lot of lithium, boron, strontium, cobalt. So, and the uranium concentration is about 3 parts per billion. But it's still, because of so much ocean water, 4.5 billion tons. In Japan, they used polyethylene fiber, and they irradiated it to create a higher affinity so it would attract uranium. So you take basically a bunch of netting of of this polymer, which looks like a white rope. You dump it into the ocean after you irradiate it, and then you leave it there for 30 days, maybe 90 days. You pull it back up again, and you're able to take out 1 kilogram of uranium. So that works. But it's currently a bit too expensive to replace mining for uranium. They think if they scale it up, they might be able to get it to $120 per kilogram to get the uranium. And uranium prices did float up quite high, but now they're back down to about $70 per kilogram, or per pound. So that kind of price means that in the ocean you have about $400 trillion worth of uranium. So I think that's a pretty good thing to go after. Also, I'm a big supporter of nuclear energy. I think that the nuclear waste is just unburned nuclear fuel, and that is far better than coal. It won't kill 1 million people a year. So how would we apply that convergence with the technology that Matt Francis talked about this morning? If you had an algae bloom that you could functionalize, where you have algae which comes up in big mass like an island floating in the ocean, then if the algae can then concentrate the uranium for you, it's similar to the polyethylene fiber. And you might be able to be clever like Matt does and figure a way to get energy into it to kind of like get the, increase the affinity. And then you can increase from the 3 parts per billion up to 3 parts per million or something like that, 1,000 times concentration. And then you would be able to use existing leach mining technology to get the uranium out. So you make your functional algae bloom, you use the tricks that Matt has to increase the affinity to the uranium, and then it sits there for a while and gets more uranium concentration. You then come up with a big scoop and take it away, and then you mine it at the concentration that you can. So then you can bring down the cost of uranium. And the more clever, yes, go ahead.
What concentration of uranium will kill your algae?
That is something I don't know. So it's just something that seems like an opportunity. I think it could work. At what concentrations, or if you have to figure out some way to pull in uranium, keep below whatever threshold, or find some way to shield your algae, bacteria, you find something that's more resistant to radiation, that can still multiply the way you want. There are techniques for increasing radiation resistance of mice, where they've injected them with gene therapy recently and they exposed them to radiation, and the control group, which wasn't treated, 58% of them died with that, and then the ones that were treated, only 90% of them died. So another convergence thing is to use gene therapy to make your bugs, your bacteria, your microbes, tougher and more resistant to the radiation. I think that they can, they can clearly handle the amount of radiation in the current seawater, and you have a lot of these extremophiles, which can extremophile microbes, which can handle really harsh conditions. So you may need to crossbreed your algae with extremophiles in order to make them tougher, or just to pick extremophiles. You have to look at your range of bugs, microbes, bacteria, whatever it is, to decide what's the best thing to do this job of mining, concentrating uranium or your other material, your cobalt, your lithium, to mine the oceans. But I think that is to look at some of the things that they're doing in the body, because they're focused on the biology of things in liquid, that could be applied to something completely different by looking at a different problem, a different opportunity, by expanding the view and saying, okay, doing really great, interesting stuff here, let's see about what's this larger problem space that we can look at to take advantage of. So again, it's something where the more, again, like that bigger toolbox, the bigger list of problems, the bigger things you know about, is like, what's the gap? Oh, it works, but it just costs too much. Then we just have to figure out, you know, we want to do it, how do we make it cheaper? And the nano scale, the smaller scale things, right now seem to work great for things in liquid and in gas. So another opportunity, again in energy, might be related to improved processing of fossil fuel petroleum products or with natural gas. That you have to do various things with your oil upgrader or with your purification natural gas or various other things that you could have opportunities to do with nanofibers or other materials. The opportunity that Gale's working on in terms of taking a nanomembrane and making desalination, removing salt from water, making that a lot more efficient, cheaper, too. So I think those kind of opportunities are big areas for convergence. Another area, if you have any questions about that, I can talk further about that one. I'm going to another way of combining current technology and other methods to, yes, go ahead. Yeah. So another opportunity that I've thought about is there's recently been the famous Google Lunar Challenge, where Google's going to pay $20 to $30 million if you can stake a robot rover, private company can stake a robot rover, onto the moon. Many people have been saying, well, this is too expensive a thing to do in the 5-year time frame that they're talking about. My solution to it, and again, it's something that is somewhat a conversion of technology and method, is that you don't create a new billion-dollar rocket the way NASA is talking about going back to the moon with. What you do is you use an existing chemical rocket, like a $10 million Russian rocket. They have a Dnepr, D-N-E-P-R, or the SpaceX rockets, and you just buy that. You get up to Earth orbit, so we know we can do that, not a problem. And then there's this thing called low energy orbital transfer. So this is something that's already been done by the Japanese. So basically you have the Earth, the Moon, and the Sun. And if you don't want to go to the Moon in 3 days, the way the old Apollo guys did, if you go in 5 months, what you do is you take your orbit and you keep going wider and wider and wider, boosting up a little bit, and then you get towards a neutral gravitational balance point between the Earth and the Sun, and then you fall over into the orbit of the Sun and the Moon. So basically, bottom line is 5 months you go from Earth orbit to lunar orbit, and you use maybe 10% of your weight in fuel instead of a bunch more. So you get up to Earth orbit with, say, 3,000 pounds, 3,000 kilograms of weight with a cheap rocket. You spend another 300 pounds of fuel to get to the moon, lunar orbit, and then you have a cheap lander, like they almost won with the Armadillo Aerospace in the last competition last week or so. Almost worked. Don't think that they won't achieve it, because they're within seconds of achieving the goal. They had to fly from one spot to another and then fly back. They kind of flew over, and then when they flew back, they crashed. But basically then, that was simulating flying down from lunar orbit to the lunar orbit to the moon's surface. So nothing fancy, just using a less used technique to get to the lunar surface. Then you just roll out your robot, which we have plenty of. We have, the lunar robots is, the relatively, cheap rovers that we have. We're building them fairly commonly. To build a lunar a robot that can run the moon, they have these cheap little cards. You can kind of it's not that much more difficult than that. So that is an area where it's just an overlooked technique, the low energy orbital transfer, and then everything else is just using stuff you already have. So basically, I think NASA should be sending, instead of spending $5 billion, $20 billion or more building a new rocket just to justify the job on the ground, they should be sending a constant stream of robotic mining, building things to the moon, and start building up all of the lunar bases, lunar mining materials, solar cells, and that kind of thing, extracting the oxygen from the lunar regoliths, and then within a few years' time, you would have a completely built-out city ready to fly your astronauts over to. You don't have to have something that lands 10 tons of stuff with your astronaut. You just fly your astronauts over light because you've already built everything there. It's all waiting for them. So then you can use the existing rockets and you go over there. So again, it's a problem which is relatively fixed, and then you find just a cheaper, better way to do it. And also, it's cheap enough for private industry to do, where if you just have a $10 million rocket, and then all you're paying new is your lander and your robot. Another area for space launch is that getting to Earth orbit is just a matter of delta V. You have to add enough speed to what you're doing to get up there. A lot of people are hoping for the space elevator, but there's ways to do that earlier. I was thinking about laser arrays. These haven't. This is again, I'm picking up an idea that's already been studied by NASA. They had an advanced ideas group, the NAIC, NASA Advanced Institute of whatever, and some guys have worked out that you could use laser arrays to launch. Old idea is that if you had a really big laser, 1 billion watts or like that, you could then launch things into orbit, or you can send them far away at very high speeds. Problem is, we don't have lasers that big. So what we do have now is lasers that are pretty big. The military is close to putting together a 100 kilowatt laser, which is just up at the edge of being interesting for them as a weapon. But what you can do with that instead is you can have 1,000, 10,000 of them together, and you can have the equivalent of a 1 gigawatt laser in order to launch things into orbit, cheap, just for the cost of electricity. And you can further enhance that with mirrors. That's again another idea from NASA Advanced Institute, where they were using mirror reflection, where you bounce the laser light back and forth between them in order to continually push the thing you're launching higher. So that basically just means that if you bounce 1,000 times, you use 1,000 times less energy. Again, the aspect of cheaper, sooner. I don't wait for the big laser. I want to be cheaper, I want to use less and less energy. So I figure out different tricks to reduce my energy requirements, to reduce the cost of what I'm doing.
Why don't you think they do that? I mean, why does NASA in particular do, the robot launching with the cheap rockets?
Right. The reason that I believe that NASA is not doing that is not because there aren't intelligent people there who could think of it, although some of them may not be thinking that direction, is because I believe that NASA is a political pork machine. To be blunt about it, is that NASA is a space, is called a space program, but really it is about getting money into the congressional districts or the states of powerful senators and congressmen. So if you look at the map of NASA facilities, you see it's all spread around into these facilities all over, right, of powerful congressmen and senators. so they can give jobs to people here. Admittedly, a lot of them, in terms of the astronauts, in terms of the scientists, they're trying hard to do things that they believe in. But a lot of that is not so that we can do something really ambitious and interesting in space, right? An example of that was that long after we knew that the space shuttle was not going to give us cheap launches, or the space station wasn't going to do interesting things, we continued to flush, $100 billion or more into those things, even when we knew space shuttle is a death trap, right? It's going to crash once every 30, once every 50, whatever times. We still kept using it. Do we have to constantly be sending people into space? No, we can send robots. But one, there's the public relations side of things, and the other is that they wanted to give jobs on the ground. I can't shut that down. I got 1,000 jobs here. So that was why. It's an unfortunate thing, but that's the way it is. I think that the astronauts clearly were heroes, right? No question about that. I think that Apollo was very inspirational and great at the time, but the whole strategy was ill-founded. Also, space shuttle got modified for the worse by the Nixon administration, other things. Again, for political reasons, not because they want to make it better or safer or whatever. And then, they put up Space Lab, it was doing great things, and let it crash to the ground. They put 50 launches into this ISS thing. You could have done most of that stuff with the Space Lab. It was working fine. But then you had to spend 15 years building this other thing. And now they've had all these problems with it, and then they're probably going to crash into the ocean, something like that, in 3 years after it's done. So it's not doing anything. The whole thing is misguided about what it is. Also, I believe that if you want to achieve something useful, like, say, space colonization, in order to really take advantage of what's out there, Apollo was never going to give you that. Apollo was basically 3 guys going on a camping trip for 3 days, right? Or some other, the space station things were 3 or 4 guys going up on a camping trip for a few months, right? And you can never really achieve anything with that scale. If you wanted to colonize, what happened in the 1600s to 1800s? In the years after Columbus came over to the New World, his second trip, he came back with several ships with hundreds of people in them. If you want to colonize, you want to do something big, you have to have scale. You have to be coming over with hundreds of people. And the chemical rocket thing, where you're just barely going up there with 3 stages and putting 0.1 or 0.01% of your mass up there, was never going to lead anywhere. And what you needed to have was either something really clever, like laser launches or whatever, or magnetic launches, or you use what you actually had that would work, which was nuclear. Nuclear rockets would have done it. But we know why, because of all the bad image of those kind of things. It actually was, you can make very safe nuclear thermal rockets to do it. But that was why, that the whole strategy plan could never have achieved anything really interesting in terms of, if you take the long-term historical future view of it, could never have achieved anything interesting. I'm trying to achieve it interesting, like with the robotic thing, in order to get around it. Trying to be clever using the stuff we have. But chemical rockets were crap. I wouldn't have to figure out low-energy launches and launching robots onto the lunar surface if we had a nuclear rocket. If we had a nuclear rocket, you just have one rocket, nuclear powered, and you dump 1,000, 10,000 tons anywhere you want, Moon, Mars, whatever. And then you don't have to be tricky or fancy and figure out how to, use a 5-month gravitational orbital transfer to get something to the moon. But it is what it is, so I try and work with what you got. So that's another thing about convergence is, if you don't have a nuclear rocket, you have to figure out something monkey with gravity and robots in order to get around the fact that you don't have what you want. So that's what I think about the convergence aspect. Another aspect is you have to recognize political realities. The politics of NASA, the politics of Medicare, it is what it is. To say, I'll do all this great stuff, and what if we change the politics? Well, the politics will change slower than technology. Andy Groves has an interesting plan for healthcare, where he's looking at creative ways to, like, if the system doesn't change, what can I do with what I got? So the first thing is to keep elderly people at home as long as possible in order to save money. Say $12 million a year instead of putting them in nursing homes. Second is build more retail clinics, which is basically integrating nurses and stuff into pharmacies. And then to automate as much as possible. Automated medical records, find a way to do cheaper automated tests and that kind of thing. And that's an opportunity for technology to make the kind of vending machine distribution of medicine easier in order to bring the cost down. Another aspect of medicine is to see that it's connected to energy and transportation. That we have 20% or more people getting sick because of air pollution. That if we, and the numbers from the American Lung Association are about 30,000 people die per year from the effects of coal air pollution. About 60,000 or so if you include the diesel from cars and that kind of thing. So you have the Andy Groves thing of doing what you can with technology to make it cheaper and better, and then you have to address the energy and the problem in the car and the pollution, and that means things like nuclear power or solar and wind. Of course, the reality is that the nuclear is here now. It's providing 19% of our electricity, provides close to 80% of France's. That probably will happen soon. But I'm agnostic to which one is used to fix it, other than the fact that I recognize that nuclear is sooner, and we should spend some time making that a lot better. So let's see. So I think the big target application areas for convergence are energy, more efficiency, more generation of it, environment, figuring out ways to clean it up using nanoscale technologies, other things, other pollution cleanups. You can remove toxic materials out of it. Communications, I think, is an area that's really good, that there's wireless and laser communication. Space access, I think there's a lot of creative ways that we can open up space. Healthcare and medicine. And again, the focus is you need to know about the physics of what you're doing, the energy in, energy out, the watts, the efficiency, the dollars. Those are areas where you can figure out, if I can make this thing 100 times cheaper, then I brought the problem 20 years earlier in the solution. I don't have to wait until this other thing gets cheaper because of technology improvement. I can bring it here now and hopefully make a lot of money doing it. And I would combine things like robotics, AI, new materials, the lasers, the wireless, magnetics, better sensors, nanoscale and MEM manipulation. So that's basically what I had. Any other questions about that?
Where are you from again?
I'm from, I live here in San Ramon, Bay Area, so about 40 minutes from here. I work in the IT industry. I'm on contract right now at Visa, helping them with budgeting and forecasting. But I've been a futurist for 25 years, longer. I have my own website, as I said, Advanced Blogspot, and I worked, I've been at Foresight and at Center of Responsible Nanotechnology. I do some paid public speaking on the future.
Since you're a futurist,
Yeah.
and you've been here for 25 years, just out of curiosity, like 20 years ago, what did you foresee?
I came in second in a Honeywell Futurist Essay Contest up in Canada, and some of the things I was foreseeing back then, one was that I assumed that, not assumed, but my projection was that Moore's Law will continue up to now and beyond, which was not a, and now we can say it's trivial, yes, it happened, right? But back then there were a lot of people who thought, oh, we're only going to go 10, 15 years. And I predicted that wouldn't be the case, that we'd continue on farther. I had some predictions around photorealism and realistic video, and how we can make, if we can make those generated images that could fool people, that you could have fake news and various other things. So I have some things to correct about that. I thought that there would be interactive movies where people go to the movies and you could have, because of the computing power, that you could have a movie that you could interact with, have alternate endings and stuff like that. It happened, but not for the ones where you go to theater and see it, but for the DVDs, for games, those kind of things. I had some projections around increased bandwidth and how you could have your own personal channels, which is kind of happening in a weak form in terms of YouTube and those kind of things. But I think I probably underestimated, and you have also the equivalent of your own channel with the blog and that. I think I underestimated the difficulty of generating content. So there's things that I missed in terms of that. I had certain projections around that back then. I also probably would have expected more things to have happened in space, but I probably didn't understand the real obstacles not being technological around that.
I came in late, but and I know you were talking about space, but
Yeah.
what do you think about the space elevator? Did you talk about that at all, nanotechnology?
Yeah, I did talk about the space elevator. My thinking is that the space elevator is, I didn't discuss it back then, but the space elevator I think is good. I think they probably might be able to get it to work. I'm interested in what's happening with something called super threads. That's basically, I think, Lawrence Livermore, National Labs, has created carbon nanotubes that are, I think there's a researcher called Wang, who created carbon nanotubes about 10 centimeters long, about 4 inches, and they've woven them into threads. And supposedly, that has nearly the full strength of the small-scale material, which would be pretty darn close to providing you the strength you need for a space elevator. But so that's a physical capability. You still have to make the carbon nanotubes cheap enough. Currently, we produce about 60 tons of carbon nanotubes, in different kinds, single wall, multi-wall. They are making more factories to produce more carbon nanotubes, and probably by 2015, we'll be making about 10,000 tons per year, which means the cost drops by about 100. Exactly how much is less clear, but you go. So you have, in order to make enough carbon nanotubes, even if you had super thread, you can't have just a little bit of it. I can't have just like this much or whatever. I need to have a bunch in order to make my space elevator. But my thinking was that, in the best case, is going to take 20, 30 years. I think in the best case, 20, 30 years. And what do you get from the space elevator? You get to send something into space for the cost of electricity. Basically, the electricity to run your little climber up to, the geostationary orbit, whatever it is. So my idea was that what are the other ways that we can radically drive down the cost of getting into space? And my thinking was I'm more in favor of laser arrays, laser array launches and mirror launches. Basically, we have almost the 100 kilowatt lasers, solid state. We can do more powerful with chemical, but you want solid state. And the efficiency is about 20%, but there's some ways maybe to get up to 80% efficiency in terms of like the energy put into the laser, how much you get out. So you need to be hooking up like your nuclear reactor to power your array of lasers. But you wouldn't have to wait to get a gigawatt laser. You just get 10,000 of the 100 kilowatt lasers, and then you launch your thing into space. You zap them, and then you hand them up there. I also was indicating that mirror.
Sorry, how would you get the payload into space using a laser? I didn't follow that.
So you'd have some kind of object like that, which would be your space vehicle, and then you'd be hitting it with lasers.
So it's like, I don't know, like a mirror or something on the
Yeah,
bottom?
you can mirror the bottom of it, something like
Okay.
that. Yeah,
Okay.
and then you're hitting it with lasers.
And you're just pushing it up?
You're pushing it up. Yeah. Yeah, so the power is all down below.
Okay.
And you're just hitting it, and it's going up. They have different versions of it. One is, you have pure laser light and heat and stuff like that, and atmosphere reacting, whatever, and you're just blasting it up. Another one is where you have some block of something or other below here that you're basically reacting, like a block of oxygen or some solid thing, and then you're making that, and then this, and because you're heating it up, it's giving off your thrust. So instead of having the reaction, you're basically saving about 10 times the weight or something like that, because the energy provided from remotely. I was liking the mirrored reflection method for laser launch, where you hit it with lasers and it's bouncing down to another mirrored surface below, and it's reflecting a few thousand times. So then you can get higher performance. But to launch it into orbit, you probably don't need to worry so much about that. And then there is still the question of, they only have done this in the lab, where they have a 10-watt laser, and they bounced it around between a couple of lab benches and like that, in order to get like a few micronewtons of force in order to make it work. But there's nothing, theoretically, where instead of a 10-watt laser, I use my 100 kilowatt laser, or I use a bunch of 100 kilowatt lasers in order to blast in between. I should get this scaling of force into it. So then there's nothing that prevents me from, if you scale it up and make it work, from replacing those terawatt lasers that a guy, Robert Forward, talked about using to send something at 10% the speed of light or 20% the speed of light to the star. You probably would do it on the moon, so you wouldn't have any atmospheric losses. But there clearly are wavelengths where you can send lasers through the atmosphere without losses, because I can see the light from another star. It came through the atmosphere, and no problem. So there's wavelengths where you can come through and see it. Another application for space that I had thought of was that, and this is taking some speculative technology, two speculative technologies, and combining them into something that might be more efficient. There is the Mini-Mag Orion rocket. Orion is a nuclear rocket. Basically, that was something that they thought about in the 1960s. Basically, you have a big metal plate with a hole in the center, and you drop atomic bombs through that hole, and then you go off into orbit. External pulse propulsion. The more PC version of that is to use subcritical explosions, about 10 tons worth of TNT worth, 5 tons worth of TNT worth. Andrews Aerospace, I think, is the one developing it. And you send that out. You probably have this in orbit already, so you don't launch it from the ground. You have it in orbit already, and then you would have the explosion blast out, and then it would be captured in a magnetic netting to propel the vehicle. So they had worked out that if you were to accelerate fuel to it, small 80-gram capsules of fuel to it, using lasers or something like that, laser sails, you can then refuel this thing on the go. So instead of capping out at 0.1 speed of light, like that, they worked out that you can get up to 10% of the speed of light. Someone else is working on something called Lorentz force propulsion, where basically you can take filaments of like carbon nanotubes and or any other wire filaments, something that looks like that, and then because they use polonium to charge it up, and then you have this Lorentz force thing in order to propel it. It's kind of a variation on magnetic forces. And then you can accelerate these small objects up to, again, 10% of the speed of light. And it's propellantless. It's not sending any chemical blasting out the back in order to make it work. And the best magnetic field to work it off of is Jupiter in the solar system. So instead of making the big lasers to refuel your nuclear rocket, you make small Lorentz force things, and they have fuel. And then you can sell it propellantless into Jupiter and send it off chasing after your nuclear rocket. And then you don't have to capture them. You just hit the back of it. And because you're hitting them with such speed and force, they fuse automatically. Because if you set something fast enough, it's going to fuse. So then it's just a matter of making sure that you make whatever it is you're pushing against tough enough to take these 80 gram or however size things, hitting at high speed into the back of this thing, and then basically that is your fusion reaction of the back, and then you're getting up to 10% speed of light. So you're using something that are kind of crude for us, crude nanotechnology, would easily make this thing, and then you're refueling a nuclear rocket off it. And you're not even refueling it, you're just sending the reaction material to it. And then you're getting up to 10% of speed of light. So the lesson is that even okay nanotechnology will get you all over space. You're going 10% speed of light, you're chugging around all over there because you can do these kinds of things. The other thing about it is that they talk about the PC version, Minimag, oh, we don't go to critical. I think that's a complete waste of time. Because if I have a 1,000-ton rocket going at 10% speed of light, and I turn that sucker around and crashing into the Earth, well, E equals mc squared, 10% of that mass just turned into an explosion. Far bigger than any piddling little nuclear bomb that we need to propel this thing. And if I got gigawatt lasers, arrays and stuff, blasting stuff, I'm worried about nuclear bombs. Basically, if I got good technology, all that other stuff, like nuclear bomb stuff, is crap, right? So people have to get around the fact that if I got the tech, I can blow crap up. The solution is we can't just stay on the Earth, because if we stay on the Earth, it's basically like, oh, we have hand grenades in our house now. Let's all stay in our house. It's not safe. If the pin will get pulled, you're going to blow crap up. You have to spread out into a city, into a larger area, so that you're safe. No amount of security is going to make you safe with this kind of technology. It's just too powerful. The only thing is you got to get spread out, so that if they do blow up the Earth, that would really suck. But we only lost 1% of our population, right? And now we punish those guys who did it, right? That's just the way it is. Like, we have accidents now. Well, Paul killed 1,000. We lost 2 million people in Iraq. If we were still hunter-gatherers and we only had 2 million people and we lost them all, well, that was it. We got nothing. But because we got 6.5 billion people and we lose 55 million every year, it's like, it's not good, but it's not civilization ending. So that's the kind of like the big thinking you got to go with, is that if you're big enough, you're wide enough, you're robust enough, what was a fatal stab to your heart is now a mosquito hit. If you're bigger, you're stronger, you're tougher, then you don't have to worry about it. And that's the only solution that there is. And to try and make it safe in a small space, like a bunch of people with knives and telephone booths, it ain't gonna work. Thank you.
Unless you're one of the 1%.
Yeah.
It sucks.
But then, if you were one of the 100%, that would have sucked even more.
That's true.